Welcome to ninth lecture of Analog Integrated Circuits Design. So in today's class, we'll continue our discussion on small signal amplifiers. What we're discussing now is CS amplifier. In yesterday's class, we looked at other two loads like triode load and current source load. So before continuing with the last variety, which is common source amplifier with a degeneration resistance, let us first compare the previous circuits and let us have a let us summarize the circuits what we have studied so far. So the very first thing what I'm going to do now is a comparison of all the circuits what we have done so far. So you all remember the very first circuit what we have seen as a common source amplifier with a resistive load. So this is input output, V in V out, and this resistance is RD. So we will look at two important things, the gain of each circuit and the output DC level of each circuit, right? So for this circuit, if you remember the output DC level, which is the voltage coming here, the output DC level is actually set by the resistance RD, and always your output DC level will be equal to VDD minus ID into RD. This is the output DC level of this circuit. And now if you write the gain expression for this, the gain can be written as minus GM into R out, and GM in this case is GM1 of the input device, considering always the input device as M1. This is M1. It is minus GM1 into R0 parallel RD if we are considering channel length modulation. Otherwise, it is minus GM into RD. This is known. So what I'm writing here is using this color, it is output DC, and using the other color, I'm writing the gain. Right. So quickly, if I move to the second circuit, it was diode connected structure. So in place of resistance, we were using a diode connected structure. Initially, we started with the NMOS diode connected. So source and drain are shorted together. This is VDD. This is M2, M1, V in node, and this is V out. Now, if I want to write the output DC level at this point, so can you guys write the output DC level and gain of this circuit also in the chat box? The output DC level is for the circuit you have the transistor M2 whose VGS is here. You can specifically write it as VGS2. So output DC level is basically VDD minus VGS2, which is appropriate way of mentioning the output DC level. R01 you can neglect R0 and write it as minus GM1 by GM2 also, right? So let me write this. In this case, I'm considering all with the channel in the modulation. Moving on, the third circuit is we just modified this. Not modified. We changed this PMOS input load, NMOS diode connected to a PMOS diode connected, and that is the circuit. So this is VDD, M2, M1, V in, V out. Now, if you look at the output DC level, you can see that this is plus minus VSG. This is also 2. So I can write it as VDD minus VSG2. So the difference is the second circuit was NMOS and now this is PMOS. That is why we write it as VGS2 and in this case it is VSG2. And for the gain remains the same. So I'll just put it is same as the previous. No difference. Now we also saw a modified version of this, but basically why we went for modification is to have a smaller overdrive voltage or should have to have a larger output swing. So that circuit I'm not bringing in here because for practical reasons that ideal current source should be realized using a transistor itself. So then how much ideal that practical current source depends on that only we can talk about the overdrive voltage ratios and other things. So I'm not bringing that circuit here. Again, triode load also I'm not drawing it here because triode load is also not widely used as amplifier. Now we saw the last one, which is a current source load where your transistor is driven into, the PMOS transistor is driven into saturation, which is a widely used circuit. So this is V in, this is V out, VDD, M2, M1, and this is biased properly, say by V bias. Now, so for all the other three circuits, if you, yeah, this is to be noted because yesterday we did not see this much. So for all the first three circuits, if you look at the output DC level, I would say the output DC level of all these three circuits, the first three circuits, output DC level. Can you tell me? Just think about this. You have actually four circuit diagrams here now. Let me mark it as A, B, C, and D. Right. Now, for the first circuit, just by visually inspecting the circuit, we can say that the output DC level is VDD minus IDRD because there is a resistance which will have a fixed voltage drop, and that will definitely bring an output DC level of VDD minus IDRD. The next one, the second circuit, you have M2 device. When that device carry a current of ID, VGS2 will be fixed. So I can say that the output DC level is VDD minus VGS2. Now the third circuit, again M2 device carrying a current of ID will have a specific VSG. So output DC level will be VDD minus VSG2. But so since we can visually inspect and clearly comment on the output DC level, we call or we say that the output DC level is output DC level for all the circuits is well defined. So what is the meaning of this? When do we say that the output DC level is well defined? When we can comment on the output DC level by just visual inspection without doing any calculation. If we can say or by visually inspecting, if we can clearly say about the output DC level, we call the output DC level is well defined. Now coming to the last circuit where you have two current sources, M1 and M2, where both of the current sources, the output DC level is not the transistor, the load transistor is not diode connected. So now what can you comment on the output DC level of this particular circuit? By just inspecting or by visual inspection, can you say that the output DC level of this circuit is so this much or this much? Can you clearly say that? Are you getting what I'm trying to say here? Yeah. So what I'm yeah, if you have questions, please post. What I'm telling here is in this specific circuit, I do not have a resistor. I do not have a MOSFET which with which I can say that okay, this much is the VGS. The only thing is there are two transistors. Both transistors are biased, and but the output DC level is not determined by the VGS voltage of any device. In such case, we will say output DC level is poorly defined. The meaning is when I say poorly defined, by just visually inspecting, I cannot clearly talk about the output DC level. That doesn't mean that this will not have an output DC level. This will have, or we have to fix the output DC level later. But by visual inspection, I cannot comment on that, right? So output DC level is poorly defined. And in such cases, and you can also think about this for all these circuits, for this circuit, this one and this one, all these nodes are a low impedance node, and only for this circuit your output impedance is a high impedance node, and the output DC level is poorly defined. So we say that, or we comment it like this: the DC level is floating. So what is the meaning when we comment the DC level is floating is the DC level of this circuit should be fixed by an external circuitry. So we have to, or we should fix the output DC level. So if you want to, as a designer, if you want to fix the output DC level, we have to actually use an external circuitry to fix it. And what is that circuitry and how do we fix all those things, we will study a little later. We call it as common mode feedback circuits. That will be dealt a little later. Now talking about the gain, you can see there is a difference in gain comparing to all the three previous circuits. The gain is GM minus GM1 into R01 parallel to R02. So what I want to say here is the output DC level of this circuit, when you have two drains tied together, is not a clearly or a well-defined output DC level. It is poorly defined because there is no resistor directly fixing the output DC. There is no transistors VGS which is directly fixing the output DC. Right? Is that clear? Any questions here? Are you guys with me? Okay. All right. Okay. If you have questions, please ask now or even at the end of the session. All right. Yeah. So we are moving on. This is what we have done, the comparison. Right. This we have done in the previous classes, but I have just written it on one place together so that we can just review it. Now moving on to the last variety, that is CS amplifier. With source degeneration. All right. Probably I think you will remember this, what you have done in your last semester AMC. If you are not remembering also, it is okay. So if you look at a transistor, say for an for example N MOSFET, if you're applying V in, you will have a current ID here, and we know that the relationship between the current ID and voltage V in is non-linear. This relationship is non-linear. And if it is non-linear, how will we mark this? We will represent this non-linear relationship something like this. In this axis it is V in, this is ID, and so how these two are related? This is nothing but your transfer characteristics, right? V in is nothing but VGS here. So till Vt there is no current, but after that there is a square law relationship existing. So this is the relationship between ID and V in. Looks like a straight line, right? This is how the current ID and voltage V in of a MOSFET is related, and the relationship is nonlinear. Now we have looked at the voltage gain of many MOSFET circuits, and we wrote that voltage gain of such circuit or all the circuits are AV is equal to magnitude. If I write it is GM into R out, or I'll write it as say capital GM into R out. The magnitude of all the circuits we wrote in this fashion, and we evaluated capital GM in all such cases as so Capital Gm in all the circuits what we have dealt before is equal to exactly equal to small gm, right? Now, let us look at this particular component of gm of a MOSFET. So if you plot a gm of a MOSFET versus Vin, how the graph will be looking at. So if this is GM and if this is Vin, so how is GM and Vin related? So if I'm increasing Vin, how will it reflect in GM? What do you think? The first graph is straightforward relationship. ID and Vin both are non-linearly related, or a square law relationship is there. What about GM and Vin? We know the relation that GM is equal to uh, mu and Cox W by L into VGS minus VT. That is what we know in general about the transconductance. VGS is V in if you have a MOSFET where the source is tied to ground. So if at all there is a variation in VGS, definitely GM also will vary. So if you how is this variation? How GM and VGS are related? VGS is V in this case. So both with this VGS and V are linearly related. When I say linearly related, it is not having a straight line starting from the origin 0 till VT there is nothing. Till VT there is no current as such. But after that, after VT, you can see that there is a after VT only we can define GM, the transconductance of the circuit, and that is linear as per the relationship. What is the relationship? GM is equal to mu and Cox W by L into VGS minus VT. Assuming mu and Cox and W by L both are not varying, the only variable, if you change VGS, that variation will be reflected directly onto GM if the transistor is in saturation region, right? I hope you will agree for all these things. Are you guys with me? Can I get a response? Okay. So, what do you understand from this particular discussion? What I have made here? Or I don't know how to reframe the question as such. You can see that. So the drain current and your voltage, they are non-linearly. They have a non-linear relationship. So that will actually result in, if you look at the gain expression, gain is having this GM term. Now, if gain is having this GM term, whatever variations happening to V in, it will be reflected in the gain. All right, Avinash, your question is GM is I out by V in. Yes, I out by V in. That is true. And if you have a transistor, if you remember, for all the circuits what we dealt before, when you have a single MOSFET where the source of that MOSFET is tied to ground, your GM I out by V in is equal to small gm of the input device. In general, we even though we write it as capital GM as the short circuit transconductance of the circuit, that will be finally that will be equal to the input device short transconductance. Is that your question or? I'm not getting. What is inversely proportional?
Sir, GM and V in, sir.
Okay.
According to this equation, they are inversely proportional, right, sir?
Mm, yeah. So whatever you have written as I out by V in this case is the small signal behavior, right? This I out by V in is a small signal, and capital GM is a short circuit transconductance. That is true. That is true. Yeah. The point what you made is right. Now, what you are seeing here is for this particular circuit, I have marked it as Vn, which is directly the VGS value. So you don't need to consider this as a small signal voltage, because we will not have such a large variation in a small signal voltage. You can see the graphs what I have drawn here, the first and the second graph, both graphs I am showing a larger variation in Vin. So that means this is not a small signal voltage I'm talking about. I'm talking about a larger variation in Vin, and that is exactly equal to VGS of the MOSFET. Right. So when you look at this relation, what I have, what I have written on the screen, what you can see now, GM is equal to mu on C of W by VGS minus VT. You will definitely see a linear variation between GM and VGS, where this VGS is a you should not consider VGS as a small signal voltage. Rather, the VGS is actually a large voltage, a large we call it as large signal variation. Is that clear, Avinash?
Yes, sir.
Yeah. You have still question?
No, sir, that's fine. I understood. So this is
Okay.
basically graph of DC level voltages, right, sir?
Yeah, DC level, or we usually call it as large signal, because we are not talking only for a small like incremental variations. Rather, we are talking about a large variation in the input signal. So that cannot be considered as small signal.
Understood, sir. Thank you.
All right. Yeah. So the whole point here, what even I also wanted to bring in here is, um, one second. Yeah. Um, okay. So as we mentioned in the previous class, you can see that gain is equal to GM into R out. Now, when your voltage varies, your GM is also varying, and your gain is varying, right? So, as I mentioned, if we are looking for a variable voltage, variable amplifier, this is perfectly fine. But otherwise, this is not fine, because gain is something what we want to have like a gain should be something which should be constant. It should not be like varying like anything, right? uh, so I think you will agree to that. Now the point here is, if I want to if I want to um, one second. All right. So you can see that since your capital GM is exactly equal to small GM, that will definitely reflect in your gain, right? Now, if you want to have lesser variation, or if you want to have um, a lesser dependency on lesser dependency of GM on gain, what should we do for this, or how should we proceed? What you can see here is input voltage Vin is linearly dependent to GM, so that is directly reflecting in the gain expression. Along with that, Vin is also having a non-linear relationship with ID. Any idea what I'm asking to you guys? All right, so let me explain that in this way. So with a single transistor where source connected to ground, we saw that Vn is a non-linear relationship with ID, and GM is actually varying in this form. Now variation in GM will definitely affect the gain, that we understood. Now, instead of using a single MOSFET here, what is the difference if I'm adding a component at the source of the MOSFET? And if I'm calling it as RS, say this is V in, and this is having a current ID. So what I did here is, instead of using a single MOSFET, I'm now using a composite device. I call this as composite device. What is this composite device? Composite device is by adding a resistance Rs to the source terminal of the MOSFET. Now my question is, by adding a resistor to the source of a MOSFET, what change will it bring? Let us study this. Let us observe the changes. Now, what will happen if I'm increasing Vin? What will happen if Vin increases? Can I get some response in the chat box? As Vin increases, what will happen to ID? Whether it will increase or decrease? It will increase. Of course, it will increase. So ID will increase. Now, if ID is increasing, ID is flowing here. So ID is flowing through RS. That means the drop across RS will definitely increase, right? So can I write it as ID into RS will also increase with respect to this? Yes, right? Now, if ID into RS is increasing, look at this node. Say if I am marking this node as the source voltage Vs, if ID into RS is increasing, definitely this Vs will also increase. I think you guys will agree with me in this, right? So what is happening? Vin is nothing but directly the Vg point. Now when Vg increases, your ID will increase. That will increase the drop across resistance Rs. That is actually increasing Vs. So as Vg increasing, Vs is also increasing. What is the meaning of that? The Vgs term will be almost remaining constant. Will you agree with me? As Vg increases in a circuit, when you place this in a circuit, as Vg increases, finally Vs is also increasing. As a result, Vgs will tend to remain constant, right? If that is the case, if I consider a loop here, how will I write it? V in minus, so this is nothing but, I'm just using a different color. This is VGS voltage. So V in is from here, from ground, minus plus. This is V in minus VGS minus ID into RS is equal to 0. That is a loop equation on the input side of the device. Right. I'll repeat again. What I'm telling here is I'm just adding a resistance RS. In the previous case, there is nothing to talk about in this fashion because there is no RS. So as V increases, ID will have a V and ID are related in a non-linear way, and ID also increases in a non-linear way when you increase V. But now in this case, uh, yeah, so in this case, when you're increasing V in, finally your VGS is becoming constant. And if you write a relationship between, can you guys hear me? All right. Yeah. So, yeah. So when you are increasing your V in, um, finally, finally your VGS is remaining it as a constant value, right? So from the relation, you can see that V in minus VGS minus IDRS is equal to 0, or when you write it further in terms of ID, I can say that ID is equal to V in minus VGS divided by RS. You may be wondering what I'm doing. I'm just explaining. I'll be explaining that now. Right. Now you can see the relationship between ID and ID, V in, VGS and RS in this case in the from this relation. So look at this expression. RS is a constant value. This is constant. From the observation, we also understood that VGS is a constant here. So what is the meaning of that? As ID increases, your V in is increasing. In what fashion? The relationship has now become linear by placing a resistor at the source end of a MOSFET. Will you agree with me? What I meant here is when you have a composite device with a MOSFET and a resistor at the source of a MOSFET, the composite device is linearized. Right. Now the relationship between voltage and current in the circuit is in a linear fashion. Any questions on that? Now, what is the advantage of having this voltage and current making linear? So, okay, so what is the advantage or what is the benefit for us as circuit designers? Let me continue with this and let me find. So, I was talking about in the previous case when there is no resistance, your ID and Vin are non-linear. GM is varying like this, though that variation will be affecting your voltage gain directly. Now, let me find for this circuit what is the GM, capital GM. So, why I need to find that separately? Because for all the previous cases when you had a single MOSFET and when you had that MOSFET connected, the source connected directly to ground, the effective transconductance was the GM of that device itself. Now we need to find the effective transconductance of this composite device, which is GM of this device. So how will I find that? So this is the MOSFET. So we know what is the procedure to find short circuit transconductance. This will be V in here, and I need to short circuit the output point, and I'll assume that there is a current I out, and I'll find what is I out by V in. That will give you capital G. We know this is the procedure what we have followed in all the previous cases. Now, let me assume that lambda is equal to 0 in this case. So, how can I write I out and the VGS value here? I know that I out will be equal to GM into VGS in any case because R naught is considered as infinity. Now, what is VGS here? VGS is equal to, VGS is actually the voltage between these two, that can be written as V in minus. So this is RS value. So the current flowing here is I out. So when I write an equation here, I can write it as V in minus VGS minus I out RS is equal to 0, or VGS is equal to V in minus I out into RS. Now substituting this back to this expression, I can write I out is equal to GM into V in minus I out into RS, or if I sum I out RS into I out, or when I take I out to the side, it is 1 plus GM RS, which is equal to GM into V in, or I can write I out by V in is equal to GM by 1 plus GM RS, right? So you'll be wondering what I'm doing here. Without resistance, we saw the relation and we saw that gain is directly depending on GM. Now by adding adding a resistance at the source end, what we want to do, or what we achieved is capital GM is equal to GM by 1 plus GMRS. Right. So if your capital GM is GM by 1 plus GMRS, will we have the same variation as before, or is there any change? My question is, so previously when you have GM equal to GM, as GM varies, your gain will have a gain also will vary. Now what we actually want to make here is, if I can make gain a weaker function of small gm, I can say that gain will not vary much. That is what our ultimate idea when we proceeded with adding an RS, right? Because in gain expression you have strong factor gm in the numerator itself, that will definitely reflect the changes in gm directly to the gain, and that is not preferred. So for that reason we added a resistance RS and observed what happened, and we obtained at a final value of capital GM. We wanted to make gain a weaker function of gm, but what happened here is the capital gm a weaker function of small gm? Can I get the response as yes or no? I think I can take some quest. Yes, yes, it is true. So how can I say that? So I'll take gm common from numerator and denominator, and I'll get cancel gm, so it is 1 by gm plus rs, right? Here capital gm is equal to 1 by 1 by gm plus rs. So we know that this 1 by gm term is very small, or even here you can do this approximation. So if your GMRS term is very large compared to 1, this can be approximated. The denominator can be written as just GMRS. That factor is 1, larger to 1. So this is approximately equal to 1 by RS. Right. So what we made here by using a composite device. When I say composite device, it is a resistance added to the source of a common source CS device. By using a composite device, we made capital GM a weaker function of small gm, or you can see that here capital GM is equal to 1 by RS, which is almost independent of small gm, right? Maybe I'll conclude this like this here. So previously when we draw yeah, this relation, the relationship between gm and vgs, you saw that the variation is like this. So in a CS device, when I say CS device, there is no in this case, when we have drawn the variation of V in and capital GM, it was something like this, like this. But now what happened? Now I have a composite device here. This is, I'll say this is composite device, and it is understood that in this context, it is understood that composite device is a MOSFET and a resistance RS. Now, if I'm asking you to draw the relationship between the GM and Vin for this device, how it will be? Now, capital GM is almost equal to 1 by RS. So, we can draw in this way. So, this is VT point. So, here also till VT there is nothing. So, after that, so your capital GM is equal to 1 by GM plus RS, right? So now you should understand one thing. In the denominator, there are two things, 1 by GM and RS. So both will have extreme values. Say for example, initially your RS, your 1 by GM term, mm, see if your GM is very small, this 1 by, okay, let me draw in this fashion. Yeah. Say for example, if you have very small current will definitely lead to a smaller GM, then your 1 by GM will be large in that case, right? So in that case, you can actually neglect this RS, considering RS as very small. So capital GM equal to 1 by 1 by GM is equal to GM, right? So at low current levels, I would say at low current levels, 1 by GM will be considering this as very large with respect to RS. Therefore, that leaves your capital GM is equal to small gm itself. That means you will have definitely some variation. Your capital GM will be actually varying. But what will happen after some time, when you have when as your Vn increases, you will have larger ID that will make 1 by GM very small compared to RS. That means this can come to one point and then it will be independent of GM, or this value will be almost equal to 1 by RS. So what we achieved here, by using a composite device, we made this GM a weaker function of small gm. Thereby what we made the circuit, we linearized the circuit. We just linearized the circuit, right? So I hope you understood this, what we did here. Right. So when I say linearized, the relationship between VGS and ID is linear in this case. So I can take questions now, because I don't know how many of you guys understood what I was talking, what I just discussed. Any questions? Yeah, I can take questions. Before that, one more point I will discuss. So we have seen, we haven't seen the complete circuit of source with degeneration circuit, right? So we drew only the initial part or the input side. This is V in, this is RS. Now this has to be terminated using a load here. So this is RD, and this is VDD, and this is the output. So this is your CS amplifier with the source degeneration. The whole point of adding a resistance at the source terminal is basically to linearize the device, thereby making gain a weaker function of GM, right? So now for this circuit, if you write the gain expression, AV equal to GM into R out, we know capital GM, we have obtained it as GM by 1 plus GM RS. What is R out? R out I can write in two form. If I am considering lambda equal to 0, the resistance looking down is infinity, looking up is RD. So R out is nothing but RD. So gain can be written as GM RD by 1 plus GM RS, or by considering the same thing, if your GMRS is larger compared to 1, this can be approximated as RD by RS. Sorry, I forgot to put this minus sign. This is minus, this is minus. Your AV is equal to minus RD by RS. Right. So compared to the other circuits, or compared to the other gain expressions, you can see that here your gain is simply the ratio of two resistors, and there will not be any varying factor in the gain. If you remember, I told for a CS amplifier in the beginning, I told that uh, to write the gain expression, there is one, I think I have told you there is a shortcut method to write the gain expression. Gain can be, if lambda is equal to 0, we can write gain as total resistance at drain, which is RD, divided by resistance looking into the source path. Looking at source, the resistance is 1 by GM, so I can write it as GM into RD, and you put a minus sign. Similarly, even the same thing can be written even for this circuit. So when you write gain for the circuit, the total resistance at drain is RD, that we wrote. Now what is the resistance seen in the source path? You have a resistance RS, and from here you can see 1 by GM. So I will write it as 1 by GM, 1 by GM plus RS, that is same as GM RD by 1 plus GM RS. So we call this as inspection method. Inspection method. So what is that method? When a lambda is equal to 0, you can write the gain as resistance at drain divided by total resistance in the source path. That's it. So if you have questions, I can take questions now. Please stay back. Thank you for joining today's class.